Let's think about time travel for a moment. Before we bend space-time into pretzels, before we build glowing machines, let me ask you something much simpler. Why doesn't your broken coffee cup jump off the floor and put itself back together? That question is the same question that destroys every time machine ever imagined. And the answer fits in one line, C equals K log W. Section 1. The simplest equation in physics time machines are always complicated. They hum, they glow, they bend space-time with rotating rings, exotic particles, gravitational vortices. In fiction, they demand impossible materials and unimaginable energy. We instinctively assume that if traveling backward in time is forbidden, the reason must be equally exotic, a hidden particle, a missing dimension, a cosmic firewall guarding the past. But the real destroyer of every time machine ever imagined is painfully ordinary. It's an equation so simple that physics students encounter it in their first year. It governs melting ice, rusting metal, fading stars, cooling coffee. It doesn't mention wormholes. It doesn't reference paradoxes. It doesn't warn about grandfathers or alternate timelines. It simply counts. The equation belongs to the second law of thermodynamics. And quietly, without drama, it states that in an isolated system, entropy does not decrease. That's it, no thunder, no cosmic prohibition, just a direction. Look around you. A hot drink left on a table cools down. It never spontaneously absorbs heat from the room and becomes hotter. A shattered glass does not leap from the floor and reconstruct itself. Smoke released into the air disperses. It does not gather back into a tight cloud. These aren't engineering limitations, they're statistical realities. The microscopic laws governing atoms don't forbid reversal. If you filmed two particles colliding and played the footage backward, the motion would still obey physics. On the smallest scales, the equations don't care which way time flows. But on the scale of cups, air, bodies, and planets, something changes, processes become directional. That direction is encoded in entropy, a measure of how many microscopic arrangements correspond to a visible state. There are far more ways for energy to be spread out than concentrated. Far more ways for pieces to be scattered than perfectly assembled. The universe drifts toward what is overwhelmingly probable, and backward time travel would require the opposite drift. It would require concentrated energy to spontaneously reconverge, broken structures to reform, thermal gradients to reverse, probability itself to move uphill. The equation never mentions time machines. It doesn't need to. Because before you design spinning rings or bend space-time into loops, you must confront a quieter truth. Every irreversible process you've ever witnessed is evidence that the past is statistically fragile and the future is statistically dominant. Section 2. Entropy is just counting to understand why the equation is so destructive. You have to strip entropy of its drama. Entropy is not rot. It is not chaos. It is not the universe falling apart. Entropy is arithmetic. In the late 19th century, Ludwig Boltzmann reframed thermodynamics in a radical way. Instead of treating heat as a mysterious fluid or disorder as a vague concept, he asked a simple question: how many microscopic arrangements correspond to what we see? His answer became one of the most important formulas in physics, equals K log W. Entropy equals a constant times the logarithm of W. The number of microstates compatible with a macrostate. That's all. Imagine a neatly stacked deck of cards. That specific order, ace to king, perfectly arranged, is one configuration. But if you shuffle the deck, you enter a realm of astronomical possibilities. Almost every shuffled arrangement looks random. The number of messy configurations dwarfs the single ordered one. If you shuffle repeatedly, you will almost never return to perfect order by accident. Not because it's forbidden, because it's statistically invisible. Now replace 52 cards with 1030 molecules, roughly the number in a cup of coffee. A hot cup corresponds to energy concentrated in a relatively narrow set of configurations. A cool cup corresponds to energy dispersed across vastly more possibilities. The cooled state has more microstates, so it dominates. The universe moves toward what has more ways to exist. That movement defines the arrow of time. Forward is the direction in which W increases. Backward would mean compressing an astronomical number of possible arrangements into one extraordinarily specific configuration. And here's the crucial point. Nothing in the equation says reversal is impossible. It simply says it is fantastically improbable. Every particle would need to trace a path so precise that even a single deviation would create a different microstate, and there are infinitely more of those alternatives than the singular past arrangement. Time travel to the past is not blocked by force. It is buried under probability. The equation doesn't argue. It counts. And in that counting, the past becomes a statistical miracle, one that the universe does not naturally repeat. Section 3. Why rewinding means rebuilding the universe at this point. A loophole seems possible. We lower entropy locally all the time. A refrigerator pulls heat from its interior and makes it colder. A construction crew assembles bricks into a building. Living cells create order from nutrients. Entropy decreases in small pockets of the world constantly. So why not build a machine that lowers entropy enough to rewind a person 5 minutes? Because every local decrease comes with a larger increase somewhere else. The refrigerator cools its interior by dumping even more heat into the room. The construction crew burns fuel, increasing entropy in the environment. Cells create order by consuming energy and releasing waste heat. Entropy can decrease locally, but only by increasing globally. The second law doesn't forbid pockets of order. It forbids a net decrease in an isolated system. Now consider what backward time travel actually demands. You are not just trying to reorganize your body into a previous state. You are trying to restore the entire environment to an earlier configuration. The air molecules that drifted across the room must return to their former positions. The photons that bounced off your walls and escaped into space must be recalled. Thermal radiation leaving Earth must reverse direction. Every causal interaction since that earlier moment must be undone. Not approximately, exactly. Because even a single misplaced particle corresponds to a different microstate, and therefore a different present. This is where the fantasy collapses. Rewinding 5 minutes does not mean isolating a human-sized bubble and resetting it. That bubble is entangled with everything else through gravity, electromagnetism, radiation, and quantum interactions. You are thermodynamically coupled to the room, the planet, and the cosmic microwave background. To restore your past state, you must restore theirs and theirs. Backward time travel is not a local repair, it is a global reconstruction. You are not stepping into yesterday. You are demanding that the universe return to a previous statistical configuration among an unimaginably vast landscape of alternatives. It is combinatorial. You are asking probability itself to reverse direction, and probability does not negotiate with ambition. Section 4, when relativity tries to help at this point, you might object entropy is powerful, but what if space-time itself provides a shortcut? What if you don't rewind the universe, you simply take a different path through it? This is where relativity enters the conversation. In 1915, Albert Einstein revealed that gravity is not a force in the traditional sense. It is curvature. Massive objects bend space-time, and everything else follows the curves. Under extreme conditions, those curves can become dramatic. And when physicists explored the mathematics, they found something startling. Certain solutions to Einstein's equations allow closed time-like curves, paths through space-time that loop back onto themselves. In theory, you could move forward along such a curve and arrive in your own past. Wormholes, if they exist and can be stabilized, could connect distant regions of space-time. If one mouth of a wormhole experiences time differently than the other, say through extreme acceleration, stepping through might mean stepping into an earlier moment. So geometry seems to offer an escape hatch. You don't reverse entropy. You bypass it, but the escape collapses under scrutiny. Even if space-time allows a loop, entropy still governs what happens inside that loop. Every physical process within the wormhole obeys thermodynamics. Every particle still occupies one microstate among many. Traveling through a curved path does not exempt matter from statistical law. And then there's the deeper problem. In the 1990s, Stephen Hawking proposed the chronology protection conjecture, the idea that the laws of physics prevent time loops from forming in the first place. As a time machine approaches functionality, quantum fields near the loop appear to destabilize, radiation intensifies, energy density skyrockets. The structure becomes violently unstable. In many calculations, the energy required diverges toward infinity, which is physics' way of saying this configuration doesn't survive reality. So even if relativity sketches a loop on paper, quantum effects may tear it apart before it can operate. Geometry tries to help, but entropy still defines probability. Quantum instability enforces consistency. And the deeper you bend space-time, the more violently the universe pushes back. The loophole doesn't close gently. It collapses under its own physics. Section 9, the equation never mentioned time here is the final twist. The equation that destroys every time machine never once mentions time. The second law of thermodynamics does not say you cannot go backward. It does not forbid wormholes. It does not outlaw paradox. It only says this: in an isolated system, entropy tends to increase. That's a statement about probability distributions, nothing more. And yet from that quiet statistical fact emerges everything we call the flow of time. We remember the past because it was lower entropy. Records form when entropy increases. Ink spreads on paper, neurons rewire, photons scatter into detectors. Memory itself is a thermodynamic process. The future, by contrast, contains no records yet. It is higher entropy waiting to unfold. The arrow of time is not written into the fundamental equations of motion. On microscopic scales, those equations are largely reversible. Run the math backward, and the laws still hold. What changes is the boundary condition. The universe began, as far as we can tell, in an extraordinarily low entropy state. From that improbable beginning, entropy has been rising ever since. That gradient defines direction. Forward is the direction in which the number of accessible microstates increases. Backward is the direction toward extreme improbability. Time travel to the past would require not breaking a rule, but reversing a gradient. It would mean moving the entire statistical structure of reality uphill. You are not violating a law in the dramatic sense. You are asking probability to contract instead of expand. And here is why that matters. The second law doesn't ban time machines the way a speed limit bans motion. It undermines them more fundamentally. It says that the configurations corresponding to yesterday are astronomically rare compared to those corresponding to today. The universe overwhelmingly occupies states with higher entropy because there are more of them. Every time machine proposal, no matter how exotic, must confront this statistical landscape, bend space-time, stabilize a wormhole, twist geometry into loops. None of it changes the combinatorics, because the equation was never about machinery, it was about counting. And when you count honestly, the past is not locked away by force. It is buried beneath numbers, so vast that reversal becomes indistinguishable from impossibility. Time machines are not destroyed by paradox. They are destroyed by arithmetic.